Picture yourself standing right now. Your body registers a sensation, something pressing upward against the soles of your feet. We've been trained to call this gravity pulling us down. But here's where it gets interesting. That's not what's happening at all. The sensation you're experiencing is actually the ground shoving upward into you. Think about that for a second. You've never once in your entire life felt gravity as a downward tug. What you feel is always, without exception, something pushing up. The floor beneath you, the chair supporting you, the bed holding you. They're all pushing. So where exactly is this mystical downward pull everyone keeps talking about? It doesn't exist the way you think it does. And there's something even more puzzling about this force we call gravity. Right this moment, our moon is plummeting toward Earth. It's been falling for over 4 billion years. Yet somehow, it maintains the exact same distance. It just keeps circling endlessly, falling but never actually getting any closer. What kind of force behaves like that? A force that supposedly pulls objects together, but somehow never actually brings them together. According to Isaac Newton's formulation, this force operates with 0 time delay. If you could magically shift Earth's position, the moon would respond instantaneously across 250,000 miles of absolute nothingness. No signal, no messenger, just immediate action. Newton himself found this concept deeply troubling. He labeled it action at a distance, and openly confessed he had no mechanism to explain how it could possibly work. But his mathematical framework was absolutely stunning. His predictions matched observations with perfect precision. So the scientific community collectively decided to stop asking uncomfortable questions about the underlying reality. That was a mistake. Let's rewind the clock several centuries. The movement of planets was a complete mystery. Copernicus had established that planets orbit the sun, but the crucial question remained, what paths do they trace through space? Enter Tycho Brahe, who constructed a world-class observatory and dedicated decades to recording planetary positions with obsessive precision. Night after night, year after year, he measured angular positions using brass instruments, calibrated to fractions of a degree. Why such fanatical attention to detail? Because nature doesn't reveal her secrets to people who guess. You have to observe carefully, measure precisely, and document exactly what you see. That's the foundation of legitimate science. Tycho's meticulous data eventually reached Johannes Kepler. Kepler's mission was to determine the geometric shape of planetary orbits. His first attempt assumed circles, the most perfect shape, according to ancient philosophy. The predictions came close, but Mars refused to cooperate. It was off by 8 arc minutes. That's 8/60ths of 1 degree. Most researchers would dismiss that as measurement noise. But Kepler understood Tycho's capability. That man didn't make 8 arc-minute mistakes. So Kepler abandoned his entire theory and started from scratch. After years of grinding calculation, he discovered the answer. Ellipses. Planets trace elliptical paths with the sun positioned at one focal point. The match with observations was flawless, absolutely beautiful. But this discovery immediately raised a deeper mystery. Why ellipses? What determines this specific shape? Meanwhile, Galileo was conducting experiments that seemed almost embarrassingly simple. He rolled balls down inclined planes. Sounds like child's play, but observe what happens. Release a ball at the top of an incline. It accelerates downward. When it reaches the bottom and rolls onto a horizontal surface, it continues moving. It doesn't instantly stop. Now imagine you could eliminate every trace of friction. What would happen? The ball would continue rolling forever at constant speed, in a constant direction. This concept disturbed people. Surely sustained motion requires continuous pushing. Surely objects naturally prefer to be at rest. No, that's the opposite of the truth. Motion is the default state. An object traveling in a straight line at constant speed requires no explanation whatsoever. That's just what objects do. What demands explanation is change. Slowing down, that's friction. Speeding up, that's a push, or changing direction. That's a sideways deflection. This principle of inertia became the first law of motion, and it immediately created a profound puzzle. Planets should travel in perfectly straight lines. That's their natural state according to inertia, but they don't. Their trajectories curve continuously toward the sun. Something must be deflecting them every single moment. But what? Isaac Newton saw the solution with crystal clarity. Planets naturally want to move straight, that's inertia, but they curve instead. Something continuously alters their motion. He called this something gravity, a universal attraction between any two masses. The strength of this force depends on two variables, mass and distance. Greater mass produces stronger attraction. Greater separation produces weaker attraction. Specifically, the force decreases with the square of the distance. Using this single principle, everything suddenly made sense. Why ellipses? Because planets are simultaneously falling toward the sun while moving sideways. The combination of these two motions produces elliptical trajectories. Kepler's observational laws emerge naturally from Newton's force law combined with the principle of inertia. Why does our moon orbit Earth? Same principle. It's falling toward Earth while simultaneously moving sideways fast enough to keep missing the target. It falls around Earth rather than into it. Why does an apple fall from a tree? Earth attracts it. Same force, identical law, just a different scale of magnitude. Newton performed an elegant calculation. He determined how much the moon falls every second, how much its trajectory deviates from a straight line. Then he calculated how much objects fall at Earth's surface. When he adjusted for distance, the numbers matched perfectly. This was revolutionary. The force pulling an apple downward is identical to the force maintaining the moon's orbit. Heaven and earth operate by the same physics. With Newton's gravitational law, the universe became comprehensible. Ocean tides occur because the moon pulls on Earth's water. Earth is spherical, but bulges at the equator because of rotation. Comets return on predictable schedules because they follow elliptical orbits. Strange astronomical observations suddenly had explanations. Jupiter's moons sometimes appeared ahead of schedule, sometimes behind. The reason? Light requires time to travel. When Earth is farther from Jupiter, light takes longer to reach our telescopes. This observation led to the first measurement of light's speed. Planets wobble slightly because they gravitationally influence each other, not just the sun. From wobbles in Uranus's orbit, astronomers predicted the existence of Neptune and found it precisely where the mathematics said it should be. For 200 years, Newton's law of gravity stood as one of humanity's supreme intellectual achievements. It explained every observation anyone could make, but there was one detail nobody could explain, one peculiarity that should have seemed deeply suspicious. Drop a hammer and a feather in a vacuum chamber. They strike the ground simultaneously, exactly together. The hammer possesses far more mass, so according to Newton's law, gravity pulls it much harder. But the hammer also has far more inertia. It resists acceleration much more strongly. These two effects cancel with absolute perfection. Not approximately, perfectly. Every object falls at precisely the same rate, regardless of mass composition. But why? Newton's theory requires mass to play two completely different roles. Gravitational mass determines how strongly objects attract each other. Inertial mass determines how difficult it is to accelerate something, and for every substance ever tested, with incredibly precise measurements, these two properties are perfectly proportional. But why should the property governing attraction and the property governing resistance to acceleration be exactly equal? Newton had no answer, just a remarkable numerical coincidence that made his equations work beautifully. Or was it actually a coincidence? Einstein posed a different question. What if it's not a coincidence at all? What if this perfect equality is revealing something fundamental about the true nature of gravity? Consider this thought experiment. You're sealed in a windowless room. You feel normal weight pressing you to the floor. Are you sitting on Earth's surface, or are you inside a rocket in deep space accelerating upward at 9.8 meters per second squared? Can you perform any experiment to distinguish these scenarios? Drop an object, it falls to the floor in both situations. Throw a ball horizontally. It traces a curved path in both situations. Stand on a scale. Identical reading in both situations. No experiment can tell them apart. This is the equivalence principle. If you genuinely cannot distinguish gravity from acceleration, perhaps they're fundamentally the same phenomenon. Perhaps what we experience as sitting motionless in a gravitational field is actually a form of acceleration. Here's Einstein's revolution. And it's going to sound completely backwards at first. Objects in free fall experience no force whatsoever. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in space stations, none of them have any force acting on them. They're moving naturally, following their inherent paths through space-time completely free, no forces, no pulls, nothing. But the apple is obviously falling, right? Yes, but what if the apple isn't accelerating at all? What if it's traveling along the straightest possible path? And it's the fabric of space itself that's curved. This is Einstein's profound insight. Gravity isn't a force pulling objects together. Gravity is the warping of space and time themselves. Massive objects don't exert pulls on other objects. They distort the geometry of the space surrounding them. They bend it, curve it, warp the very fabric of reality. The apple isn't being pulled groundward. It's following the straightest possible trajectory through curved space-time. But near Earth's surface, space-time is bent. So straight ahead points toward Earth's center. You standing on the ground aren't being pulled downward. You're attempting to follow your natural trajectory through curved space-time, a path that points toward Earth's center. But the ground blocks your way. The ground shoves you upward, preventing you from following that natural path. That's what you experience as weight. Not gravity pulling down, but the ground pushing up, deflecting you from your natural trajectory through curved space-time. Einstein made a testable prediction. If gravity is truly space-time curvature rather than a force, then light should be affected too. Light has zero mass. In Newton's framework, gravity shouldn't affect light at all. But if gravity is the curvature of space itself, then light traveling along the straightest path through curved space must bend. During a solar eclipse, astronomers measured star positions near the sun's edge. The stars appeared displaced from their actual positions. Starlight had bent while passing near the sun, exactly as Einstein's equations predicted. This phenomenon, gravitational lensing, is now observed routinely. Massive objects bend light from distant objects behind them, creating distorted images, direct evidence that space itself curves in the presence of mass. Astronauts orbiting Earth appear weightless, floating freely. Zero gravity up there, right? Wrong. The gravitational field at orbital altitude a few hundred miles up remains almost as powerful as here on Earth's surface, approximately 90% as strong. So why do astronauts float? Because they're falling. The capsule falls, everything inside falls toward Earth constantly, but they're simultaneously moving sideways at tremendous velocity, roughly 17,000 miles per hour. As they fall, Earth's curved surface drops away beneath them. They perpetually miss the planet. They fall around Earth instead of into it. Everything falls together at exactly the same rate. So there's no sensation of falling, no weight, no perception of up or down. It feels identical to floating in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating in empty space because they are the same thing. In free fall, no force acts on you. You're simply following the natural geometry of curved space-time. Think about Earth's surface. It's curved, but standing on it, it appears flat to you. Here's something remarkable. Why is Earth spherical in the first place? The usual answer is because of gravity, but not in the way most people imagine. It's not that some force pulls everything toward the center. Sculpting Earth into a sphere It's that space-time around Earth's mass curves equally in all directions. Every piece of rock, every molecule of water, attempts to follow the straightest path through that curved geometry. When everything follows those curves from all directions equally, you inevitably get a sphere, the only shape where every surface point is equidistant from the center. Earth is round because that's the method, the result when matter follows curved space-time. The shape emerges automatically from the geometry. An ant walking what it perceives as a straight line on Earth's curved surface actually traces a curve. But from the ant's perspective, it's traveling perfectly straight. That's exactly what's happening with everything near Earth. Except it's not just space that curves. It's space and time together, merged into space-time. Massive objects create deformations in space-time, depressions, wells, warps in the fabric. The sun creates a profound well. Earth creates a smaller depression. Even your body creates a minuscule well, too small to easily measure. But it exists. Objects moving near these wells naturally follow the curves, not because anything pulls them, but because they're following the straightest possible paths through curved geometry. The moon orbits Earth because it's following the natural geometry of curved space around Earth. In that geometry, the straightest path forms a circle. An apple falls because it's following curved space-time near Earth's surface. In that curved geometry, straight ahead through time points toward Earth's center. When you throw a ball, it traces a parabola, not because gravity pulls it downward, but because it's moving through curved space-time. And straight lines in curved space appear as curves to you. You're standing right now. You feel weight. In Newton's picture, gravity pulls you down and the floor pushes you up. Two balanced forces. In Einstein's picture, only one force acts on you, the floor pushing upward. But if only one force acts, you should be accelerating. And you're accelerating upward constantly. The natural path through space-time points toward Earth's center. That's the free fall trajectory. But the floor interferes. It pushes you upward, deflecting you from that natural path. You're like someone standing on the floor of an accelerating rocket. The floor pushes. You feel weight, not from any downward pulling force, but from being accelerated away from your natural path. The apple hanging in a tree is also being pushed upward by the branch. When the branch breaks, that push ceases. The apple is suddenly liberated to follow its natural path through curved space-time. It falls, but the apple isn't accelerating in any meaningful sense. The apple is finally free to move naturally. You standing on the ground are being continuously accelerated upward by the floor, pressing against your feet. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Once you grasp gravity as geometry, extreme phenomena become comprehensible. A star is essentially a colossal sphere of gas. Its mass creates a deep depression in space-time. Natural paths in that curved space point inward. What prevents collapse? Pressure from nuclear fusion in the core, pushing outward. It's a balance. When nuclear fuel exhausts, pressure drops, balance breaks. The star collapses inward. If the star is sufficiently massive, collapse continues until matter compresses to unimaginable density. Atomic nuclei emerge. Electrons are crushed into protons. What emerges is a neutron star, nuclear material compressed to city-sized dimensions. A teaspoon of this substance would weigh 1 billion tons on Earth. For even more massive stars, not even neutron degeneracy pressure can halt the collapse. Space-time curves so severely that all possible paths lead inward. Even light cannot escape. This is a black hole. Near a black hole, space-time warps so drastically that light itself, following the straightest possible paths through this geometry, spirals inward and never emerges. We cannot see black holes directly, but we observe their effects. Matter falling toward a black hole accelerates, heats to millions of degrees, and radiates enormous energy before vanishing across the event horizon. All from one idea. Mass curves space-time, and objects follow those curves. From this single principle, everything follows. Planetary orbits, ocean tides, the precession of Mercury's perihelion, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, black holes, gravitational waves rippling through space when massive objects collide. The same principle explaining lunar orbits also explains the largest structures we observe: galaxies, galaxy clusters, the cosmic web, universal, elegant. The pattern in the smallest piece reveals the design of the entire tapestry. Newton's equations remain beautifully effective for practical purposes. We use them to launch satellites, calculate orbits, predict eclipses. They're simpler than Einstein's field equations and accurate enough for most applications. But Einstein revealed what gravity actually is. Not a mysterious force pulling objects together across empty space, but the curvature of space and time themselves. Mass tells space-time how to curve. Curved space-time tells objects how to move. When you step on a scale, you're not measuring a downward pull. You're measuring how forcefully the scale must push to prevent you from following your natural path through curved space-time. When you watch something fall, you're witnessing an object finally free to follow the geometry that mass has woven into reality's fabric. When you observe the moon, you're seeing an object following the straightest possible path through curved space around Earth, a path that appears circular because space itself is curved. Curved space brings objects together. That's what we call gravity, not a force. Geometry. And that understanding is far more beautiful, far more profound than any mysterious pull could ever be.